using atomic orbitals of the bound atoms. Pairs of electrons localized on a specific atom are called lone pairs. Electron pairs found in the space between the atoms are called bonding pairs. So, can we predict the number and types of bonds an element can form? So, we're going to look at our valence electrons. Those are going to determine the chemistry of an individual element. Lewis symbols represent the valence electrons of an atom as dots arranged around an atomic symbol. So our valence shell elements, we get into those D guys again, it gets a little bit funky. Our parts of the LE model is going to be a description of the valence electron arrangement in the molecule using Lewis structures. Then that's going to give us our 2D interconnection between our atoms. We'll then figure out the 3D structure, how that molecule looks in three-dimensional space using a model called the valence shell electron pair repulsion model. And that's just simple electrostatics. Electrons don't want to be next to each other. Atoms, which are surrounded by electrons, don't want to be next to other atoms. A description of the type of atomic orbitals used by the atoms to share electrons or hold lone pairs. So we'll talk about what we call sigma and pi bonds and look at some of the bonding structures and the terminology for that. Lewis structure shows how the valence electrons are arranged among atoms in a molecule. It's named after Gilbert N. Lewis. Atoms are going to achieve that noble gas configurations. They're going to be central to the formation of a stable compound. Lewis theory implies that the positions of the ions in a crystal lattice are critical to the stability of the structure. It's going to predict that moving ions out of position should therefore be difficult, and ionic solids should be hard. Ionic solids are relatively hard compared to most molecular solids. It implies that if the ions are displaced from their position in the crystal lattice, repulsive forces should occur. And it predicts that the crystal will become unstable and break apart if you do manage to dislocate them. Ionic solids are brittle. When struck, they shatter, right? You guys have all smashed salt crystals before. Lewis theory also implies that in an ionic solid, the ions are locked into position and cannot move around. It predicts that ionic solids should not conduct electricity. To conduct electricity, a material must have a charged particle that are able to flow through the material. So ionic solids, when they are a solid, do not conduct electricity. Now, if you dissolve them, they will. It implies that in the liquid state, or when dissolved in water, the ions are going to have the ability to move around. It predicts that both a liquid ionic compound and an ionic compound dissolved in water should conduct electricity. Ionic compounds conduct electricity when in the liquid state or when dissolved in water. So our electron-dot structures are also called Lewis structures, are a representation of an atom's valence electrons by using dots and indicate the placement of dots of how the valence electrons are distributed in the molecule. You will call them Lewis structures because calling them electron dots is so high score. So let's look at carbon. So here is the electronic structure for carbon. Carbon's got 1, 2, 3, 4, 5, 6 electrons, but our Lewis structure is only going to show the valence electrons, so our 2s and 2p electrons, we've got 1, 2, 3, 4. Now, it doesn't matter in our Lewis structure for right now how we choose to draw these and distribute these around these bare atoms. You can draw it as 2 together, representing these guys, and then 1 for each of these lone pairs. You could do it as 1, 2, 3, 4 around the carbon. Right? We're going to put them into groups of 2, right? Pairs of electrons. So in oxygen, right, you've got a pair, and you got a pair, and then 2 singles. Right? Only represent the valence electrons. We don't care about these, right? If we talk about something like rubidium, right? Rubidium, even though it's got a lot of inner shell electrons, we only care about this one s, right? So we get all of our 1s's are going to have 1 dot. All of our things that have an s2 configuration, 2 dots, right? And see how these guys are separated rather than being as a group. It kind of won't matter when we start building these. How you choose to do that, either way is fine. Boron's going to have 3. Everybody in this group 3A or 13 is going to have 3. Everything in the carbon column is going to have 4. Everything in nitrogen is going to have 5. Oxygen 6. Fluorine's column 7. And in our noble gas configuration, all of our noble gases will have 8, with the exception of helium. Right, so when we write these Lewis structures, only the valence electrons are included. Our dots represent electrons, and when we draw these Lewis structures, right, for a Lewis structure of bromine, we know that we've got an ion, right? So we've got an ionic charge on our bromine. It's a -1 charge, and our potassium is going to have a +1 charge. So what will happen is that our potassium plus has no valence electrons, and our bromine minus has a full valence shell. 1, 2, 3, 4, 5, 6, 7, 8. So bromine started with 7, picked up 1. Our potassium, which is a +1, had 1, it disappeared. Okay? Writing our Lewis structures for covalent compounds is a little trickier because now we're talking about sharing electrons. So we're going to do something called the duet rule. A stable H2 molecule is formed by the combination of 2 hydrogen molecules. Each hydrogen has 1 dot for 1 electron, and then when we combine them, they're each going to share that electron like we saw before. They're sharing those 2 electrons equally between them. There's an overlap between them, and so we can draw 2 dots in between them, or we represent that as a line. And so each line that we get that represents a single bond represents 2 shared electrons. Let's look at fluorine. Right? We also still want to keep our octet rule. Things are going to form stable octets. So elements form stable molecules when surrounded by 8 electrons. So here I've got 2 fluorine molecules. Each fluorine is going to come in with 2, 4, 6, 7 electrons. They're going to share these red electrons, right? And so we've got blue lone pairs, 2, 4, 6 lone pairs around this fluorine, 2, 4, 6 lone pairs around this fluorine, and we've got a bonding pair in between. Right? And it's just a little bit awkward when we start drawing these bonding pairs. So each fluorine's got a bonding pair with 2 dots in between it. They're sharing that. If we go to something like oxygen, right, oxygen's going to come in with 2, 4, 5, 6 electrons on each oxygen, and they're going to share 4 electrons in between each one. So it's going to form 2 bonds, or a double bond. And if we look at nitrogen, which is coming in with 2, 3, 4, 5. To complete its octet, it needs to share 3 electrons, so it's going to form a triple bond. We're going to use lines to make this less tedious, and we're going to oftentimes leave off those lone pairs of electrons in our structural formula, just because once you've done enough of these Lewis structures, you know that that oxygen is going to have its completed octet, right? So like here where we've got this double bonded oxygen, it's just kind of implied that there are extra electrons, enough of them to make that complete octet, right? Sometimes, like in nitrogen though, you might leave those on to indicate that those electrons are there. So let's look at this oxygen, right? I've got 2, 4, and then we would have 6, 8. We'd have 2 lone pairs on each oxygen here. Those lone pairs are drawn out on the nitrogen. We're going to have 2 electrons, and then each line counts as 2. So 2, 4, 6, 8 on this nitrogen, and then on this nitrogen over here, 2, 4, 6, 8. Right? Each nitrogen is a happy nitrogen. So we got a problem-solving strategy. So we got steps for writing these Lewis structures. First, you're going to pool all of your electrons together. You're going to sum all the valence electrons from all the atoms. Then you're going to hook them up. You're going to use a pair of electrons to form a bond between each pair of bound atoms. And then you're going to take your leftover electrons. You're going to arrange the remaining electrons to satisfy the duet rule for hydrogen and the octet rule for the second row elements. Right? So if I look at the number of valence electrons, they're going to be stable across our groups. 3A is always going to have 3. 4A is going to have 4. 5A is going to have 5. 8A is going to have 8. 7A, those are halogens, are going to have 7. Right? And that's going to determine the number of bonds they preferentially will have. We can force more or fewer bonds, and we'll talk about that when we discuss formal charge. Right? Because you can have single bonded oxygen or triple bonded oxygen, but an oxygen kind of wants to have 2, right? Like an H2O. So it's got 2 bonds, 2 single bonds. It could be a double bond, like oxygen bonded to an oxygen, but oxygen kind of wants to have 2 bonds. Boron wants to have 3 bonds. Carbon wants to have 4. Nitrogen wants to have 3. Oxygens want to have 2. Halogens want to have 1. Our alkali metals going to want to have 1, and our alkali earths are going to want to have 2. Right? So we've got the same fixed number of valence electrons, and that is going to determine the number of bonds that we're going to use. right? For our third row and greater atoms, there may be violations of the octet rule, right? So if I'm trying to form something that is like triiodide or like sulfur hexafluoride, there might be things that are going to have what we call an expanded octet. For things that are small atomic masses, like things below boron, they're going to have like a deficient octet, right? Helium is, if it formed a bond, would not form an octet. Hydrogen is going to form that duet. Lithium and boron are going to form a suboctet. And then you're going to want to put the electronegative atom usually in the middle. Right? So you think about something like H2O. You're not going to form it as HHO. You're going to put the O in the middle. This carbon with 4 hydrogens on it, carbon's going to be more electronegative than hydrogen. Carbon goes in the middle. All right. So step number 3 is you're going to assign electrons to the terminal atoms. So you're going to work on the outside in. So sum up, right? Pool all of our electrons. Then we're going to hook things up by forming single bonds. Then we're going to take our leftover electrons and we're going to do the outside. And then we're going to put some electrons on the inside. If you got any left over, you're going to put them on the central atom. If you are unhappy, you do not have a complete octet, then you are going to form a higher order bond, like a multiple bond, a double bond, or a triple bond. Right? You're going to borrow some more electrons. Right? So it's going to help a brother out. It's going to be like, oh, hey, I see you don't got a full octet. I got a lone pair. We're going to share. Right? So let's do some examples. Let's draw the Lewis structure for water. So we're going to start off with water. We've got 2 times 1, that's coming from the hydrogen electrons, and then 6 electrons for a total of 8 valence electrons. First thing we do is we're going to put our electronegative atom in the middle, and then we're going to draw a bond between each thing. So we've got 4 electrons that we have used. We've got 4 electrons used over. We don't need to do anything else to the hydrogen. We're going to put them around the hydrogen duet is satisfied. We're going to put the rest of the electrons around oxygen, 2, 4, right? So now we've got 2, 4, 6, 8 electrons around oxygen. That's a happy oxygen. We got 2 electrons around this hydrogen. He's happy. And 2 electrons around this hydrogen. She's happy. Right? Let's do chloroform. Right? So we're going to come in with chlorine. Chlorine's got 7, so we'll do 4 times 7, 1 for each chlorine, and then 4 for the carbon for a total of 32 valence electrons. Right? Here, we're going to put the carbon in the middle, and we'll put the chlorines on the outside. So chlorine pretty much only forms 1 bond. It's really unlikely that you're going to see a chlorine with 2 bonds. Fluorine will never form a double bond or 2 bonds. Hydrogen will only ever form 1 bond, right? So those are some good rules to kind of keep in your head. Like, don't stick 2 bonds on hydrogen. Don't stick 2 bonds on a fluorine. Fluorine is always going to complete its octet. Chlorine is pretty much always going to complete its octet. Same thing with oxygen. Oxygen's really going to try to complete that octet either by bonding or forming lone pairs of electrons. So once we got our 32 electrons, we're going to use 2, 4, 6, 8 electrons. That's going to leave us 24 electrons left over. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24 electrons left over. So we're going to use all of our electrons to fill up these chlorines in their outermost shell. So we're going to form that octet for chlorine. If I look at chlorine here, this chlorine's got 2, 4, 6, 8. This chlorine's happy. All those chlorines are the same. I look at carbon. Carbon sees 2, 4, 6, 8 electrons. The carbon is happy. Right? If we are dealing with an ion, right, we're still counting up the number of electrons in that molecule. Right, so here it's H3O plus. So we've got 3 electrons coming in, 1 from each hydrogen, 6 electrons coming from the oxygen. It's a plus charge, so we take 1 away. We've got 8 valence electrons. We still do the same steps in terms of hooking up our atoms with our backbone. So our oxygen is in the middle. We've used 2, 4, 6, right? These hydrogens are all happy. We're going to put our lone pair, our remaining 2 electrons as a lone pair around the oxygen. We'll put this guy in brackets, and we'll put a +1 charge to indicate it's an ion. Yep. Let's do one for CH2O. right? So here we've got carbon is going to come in with 4. We've got 2 hydrogens at 1 each and 1 oxygen at 6 electrons for a total of 12 valence electrons. In step 2, we build the backbone, put the carbon in the middle, 1 bond to oxygen, 1 bond to hydrogen, another bond to hydrogen. We used 6 of our electrons. Now we're going to go from the outside in, right? So we're going to do 2, 4, 6. I've used up all my electrons, but look at this carbon, right? This carbon isn't happy. My oxygen's happy. 2, 4, 6, 8 around my oxygen, but my carbon only has 2, 4, 6. So what's going to happen is I need to take some of these electrons here, and I'm going to bring them down, and I'm going to form a double bond. Right? So my lone pair of electrons is going to be shared with my electron deficient carbon. So now looking at my carbon, it's got 2, 4, 6, 8. Carbon is happy. I look at my oxygen, it's got 2, 4, 6, 8 electrons. It's happy. And then carbon is happy with just its 1 bond. Right. Let's draw the electron structure for sulfur hexafluoride. Sulfur hexafluoride is pretty cool stuff. You can like Google the Mythbusters on sulfur hexafluoride where they floated like a little aluminum foil boat on it, and it changes the pitch of your voice really low, and it's fun stuff. So sulfur hexafluoride, our sulfur is coming in with 6 electrons for my sulfur, and then 7 times 6 for my fluorines. So I've got 48 valence electrons. I'm going to start off doing 2, 4, 6, 8, 10, 12. So 12 were used in bonding. I've got 36 that are left to go around. So each fluorine is going to get 6, 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. So all of my fluorines are happy. They've got 8. Sulfur here has an expanded octet. Right? It's got 2, 4, 6, 8, 10, 12 electrons that are stuck on that sulfur. So this is an example of an expanded octet. It can do that. It's actually kind of hijacking some stuff into the d orbitals, and we'll see what's happening with that a little bit later on in this chapter, but it is going to form an expanded octet. There's none left over for sulfur. If I'm drawing iodine trichloride, I've got 7 for the iodine, 3 times 7 for the chlorine, so 28 valence electrons. I'm going to put my iodine in the middle. I'm going to use 2, 4, 6 right away. I'm going to use 2, 4, 6, 8, 10, 12, 14, 16, 18 around the chlorine. I've got 4 that are left over. Those remaining leftover electrons are going to go around the iodine. All right, so our iodine is also going to have an expanded octet. Pretty much any time you're going to do multiple bonding with one of those halogens, it's going to be an expanded octet. All right, so the remaining ions go around the central atom. Let's do some other real quick examples. So we'll do HF, hydrogen fluoride, nitrogen gas, ammonia, NH3, methane, CH4, chloroform, CH4, and NO plus ion. Right? So our strategy, we're going to apply the steps of drawing a Lewis structure. You draw your lines to indicate your shared electrons, dots to indicate our non-bonding electrons. And so our HF, we're going to start off with 8. We use 2 to bond. We've got 6 left over. We end up with H with a single bond to a fluorine, 2, 4, 6 around it. They're all going to check out. Our N2, we're going to do 5 plus 5, 1 for each nitrogen for 10. We single bond to that nitrogen. We've got 8 electrons remaining, but we're going to have to bring some down from our lone pairs to form higher order bonds. So we're going to end up with a double bond, with a triple bond between our nitrogens, 2, 4, 6, and a lone pair, 8 on each nitrogen. In our ammonia, we're going to do 5 for the nitrogen, 1 for each hydrogen for a total of 8. When we hook up our backbone, we use 6. We've got 2 left over, so we're going to have our nitrogen in the middle, 2, 4, 6, and a lone pair makes 8. Our methane, which is one of our alkane groups, you're going to see stuff like this quite a lot when you start doing organic chemistry, as carbon with 4 bonds on it. As soon as you see 4 bonds on your carbon, you know it's a happy carbon. My hydrogens all satisfy their duets. I've got 8. I've used 2, 4, 6, 8. My carbon is happy because it's got 2, 4, 6, 8. My hydrogens all complete their duets. Carbon tetrafluoride, I've got 4 for the carbon, 4 times 7 for the fluorines, 32 total. Here I've used 2, 4, 6, 8. I got 24 left over. Those are going to go around the outside. Fluorine is always going to only form a single bond, and it's going to complete its octet with 2, 4, 6 lone pairs on it. So, if you see fluorine on the outside, it's going to do this, right? NO plus, we're going to start off with 5 for the nitrogen, 6 for the oxygen. We're going to take 1 away for that plus charge. All right, so starting with 10, we use 2, got 8 left over, and we're going to do something similar like what we've seen with this N2 molecule, where we're going to need to bring some down. We're going to get nitrogen with a lone pair, that's 2, and then triple bond, 1, 2, 3. All right, so it's going to form 8 around the nitrogen. Same thing with the oxygen. Oxygen is going to be triple bonded with a lone pair, so it's going to be 2, 4, 6, 8. And we'd have to put this guy in brackets and put a plus charge on here. So nitrogen kind of wants to form 3, and that's a pretty happy nitrogen. That oxygen, as we will find out, is a little bit unhappy. But we'll talk about that when we do formal charge. So let's do some quick Lewis structures here. So for our hydrogen, right, we're going to come in with 2. It's just going to look like this, H and H, right? 2 electrons. We're done. For our fluorine, all right, we're going to start off, and we know our general rules for fluorine, right? We've used 2. It's going to start off with 14, 7 and 7. We use 2, 4, 6, 8, 10, 12, 14, oops, 2, 4, 6, 8, 2, 4, 6, 8. So let's delve into some exceptions to this octet rule. Boron is 1. Boron tends to form compounds in which the boron atom has fewer than 8 electrons around it, so it's not going to have a complete octet. It's